Okay, good morning. So last week of classes, I guess is project 3, project 2. Project 2 going okay? Any questions? Yes.
So I was looking at my Newton lines, and like the baseline case you gave us had a constraint on moment coefficient. Would you recommend putting a constraint on that? Like, would that help the design at all, or is there any kind of requirement?
Okay, so there's a Newton line for CM0. You should keep it. If you remove the specification for pitching moment, it'll really be a poor airfoil. For cambered airfoils, you really need this. And I think if I remember, we did talk about there are some lines that you almost that are essential, and without them, the airfoil is going to be very hard to design. Okay. So I think the CM is CM0 set for minus 0.09, right? This is probably pretty close to what you want for the baseline airfoil. I think I haven't given any problems where you change this, but for the most part, if you leave this, you can change it a little bit if you want to alter something about the velocity distributions, but this is in the ballpark of where it should be. Okay, no more questions. So let's continue on with so in the last class we were talking about log z, and I'll just show these from the last class. So we talked about how log z has got multiple values, and there's something called the principal value branch. So if you start from z and you go around in a contour not enveloping the origin, then you will come back to the same z. But if you go around the origin, log z will change by plus or minus 2 pi I depending on the direction in which you go. So that's something like an analogy I can think of is a parking deck, where you have a spiral or a helical roadway of some sort. So if you go around one circle, you'll go up by one floor, right? But if you don't go around the origin, you just walk around in the road itself, you'll come back to the same place. So let's resume from there. So I'm going to continue using my notes from the previous year to keep things moving along because we have a time constraint. So continuing with log z, if you want to take the derivative of log z, d over dz of log z is 1 over z. And so because we talked about how there is a connection between log z and how circulation behaves for a lifting body. So there is a clear analogy between log z and circulation for a closed contour in a fluid. So just like in log z, if you go around like this, log z doesn't change, but if you go around in a contour like this, log z increases by 2 pi I. right? So just like that, this is, if you have a lifting airfoil, if you take a contour and do integral v dot dl, that will be equal to 0. But if you take a contour and go around like this, integral v dot dl will be equal to circulation. So that's the connection, and this will come in useful later on. Okay, so we talked about complex function, and there is also a geometric significance to this, and this is called complex mapping. Okay, so suppose we take a complex function zeta of z. Okay, so imagine a z plane, so z is x plus iy. So if you transform, or if you map the complex function zeta of z and put it on the zeta plane, so this is the zeta plane, this is the z plane. So zeta is psi plus I eta, right? So every point on the z plane will correspond to some point on the zeta plane. So you throw in, say, z equals 2 plus 3i, that will be this point. You put that in here and you get these psi and eta values, and that might turn out to be some point here. Like that, if you take a curve, let's take some curve and we'll call it CZ. Okay, so every point on this curve will map to some point on the zeta plane, and so that will form another curve. And this curve is, we'll call it C zeta. So the way we refer to this is the point z maps to point zeta, and curve CZ maps to a new curve C zeta. So that's the general idea. So let's look at some transformations, some simple transformations that are well known and used in various circumstances. Okay, so one of the simplest transformations is zeta is z plus b, where b is some complex constant. And so if you take any curve, this is just a translation. So this will get translated by some complex number b. So this b will be, let's say this b is c plus id, then this is c and this is d, right? So this just gets shifted. So everything will remain the same, it will just move. Another mapping or another transformation is this zeta equals a times z, so where a is some complex constant. And so what happens with this is it does a scaling and a rotation. So let's say you have some rectangle here. This rectangle will get scaled and it will get rotated. The amount by which it will get scaled is by the magnitude of this complex constant a. And the argument of a is the angle by which it will get rotated. And so this is a kind of interesting thing because it's used in so many places. There was a time when, well, let me finish the next transformation and then we'll talk about that example. So now we can add these two transformations, right? So the next simple transformation is the sum of the previous two transformations, a times z plus b, where a and b are complex constants. So here you'll have translation, rotation, and scaling. So this, if you draw a rectangle, that will get scaled by magnitude of a, and it will get rotated by argument of A, and then this whole thing will be displaced by some value by the complex number B. So this is at least the way it used to be. I don't know if it's still that way, but in MATLAB there is a function called quiver. So, quiver, have you ever used quiver? Many of you probably have, where you can draw some, like, let's say you have data for flow past a circular cylinder or something. You can draw arrows like this. That'll be like u and v velocity. It's essentially an arrow plot, right? So the way it used to work is they would have the basic arrow shape like this. So let me draw a complicated arrow. So let's say you have an arrow shape like this. You can just define it by 1, 2, 3, some 7 points, right? If you draw a line through these 7 points, you'll get an arrow. Now, anytime you want to put an arrow somewhere here, and you know the scale, you know the magnitude of the velocity, and you know the rotation, and you know the point, you can just use this A plus IB, and you will get an arrow like this. Right, so this is one example of where these transformations are pretty neat, they're pretty useful. And then there is this transformation. This is zeta equals 1 over z. So the problem with this is, it is at z equals 0 there is a singularity, but then everywhere else it's well defined. So 1 over z is well defined everywhere except at the origin. And the way this works is, let's say in the z plane you have a point here. In the zeta plane, what this does is it will mirror this about a unit circle. So if this distance is r, the new point is at a distance 1 over r, and then it will get mirrored in the x-axis. So the new point will become here. So in other words, you take this point, mirror it about the unit circle, and then mirror it about the horizontal axis, and that will be the new point. So these are some example transformations, and we'll kind of use some of these things in our complex mapping as we go forward. Okay. So when you map using analytic functions, that kind of mapping is called conformal mapping. So essentially we are going to use these transformations and transform one shape into another shape. And where we are going with this is, eventually we want flow past an airfoil. An airfoil is a fairly complicated geometry, but then we know flow past some simple shapes like flow past a circular cylinder, right? So we'll employ these kind of mappings to take the circle and morph it into an airfoil, and the flow will also get mapped, and then we'll have the flow solution for flow past an airfoil. It's a kind of very abstract way of thinking, but it turns out that there's all this practical application. So whenever you do mapping with analytic functions, that kind of mapping is called conformal mapping. And the reason that is true is that all angles are preserved in such transformations. And that's why it's called conformal. So let's say you have in the z-plane you have a curve CZ, and then let's say you have another curve that I'm showing with this dashed line. And let's call this CZ1. Then if you map this point and this curve, maybe you'll get something like this. This might become the mapped point, zeta, and the curve CZ gets transformed to C zeta, right? It's some curve. Now this angle, so this curve CZ1 will get mapped like this. C zeta 1. So this becomes C. So this curve CZ1 will get mapped to C zeta 1 in such a way that at this point this angle is preserved. And so let's call this angle alpha. This angle will also be alpha. So it's like a net. You take this net and you deform it, but at every point you have a corresponding point on the other plane. So whatever angle you had in this plane at that point will be the same angle in the other plane at that corresponding point. So that's why it's called conformal mapping. So let's see how that works out. So let's take this point Z and we'll take a small dz, okay? We'll take a neighboring point somewhere and we'll call that vector as dz. So the mapped versions of Z and that arrow are here. So zeta is the mapped version and the arrow dz, delta z becomes delta zeta. Now we know that delta zeta is the derivative of the transformation d zeta dz times delta z. Okay, so what does that mean? So remember, this is one complex number multiplying this complex number delta z, right? So if you multiply by some constant, this delta z essentially gets scaled and rotated. So the scaling is this. So the magnitude of delta zeta is multiplied by is delta z multiplied by this. So this is the amount of scaling. But then rotation is angle that delta zeta makes is angle of delta z plus this argument of d zeta dz. So in other words, delta zeta is a magnified version of delta z and it's rotated by argument of d zeta dz. Is this making sense, the argument stuff? So if not, go and review those 2 pages of complex variables notes that I put on Moodle. Then you will see what is the meaning of argument. Okay, so then the thing is that this d zeta dz, this is the derivative of the transformation. D zeta dz at this point is independent of the direction of the contour CZ, right? So we could have taken the contour this way or this way or this way or any other way. That's the meaning of analytic function. An analytic function is one where the derivative does not change with the direction in which you approach Z. So that means if you take this point Z and take one CZ like this, that will get transformed to some C zeta like this. If you take another point here, CZ dash, that will get transformed to some C zeta dash, but the angle between them will be preserved. So in other words, analytic function preserves the angle between any 2 curves passing through Z as long as d zeta dz is not equal to 0. So this is why it's called conformal mapping. The angles they conform from one plane to the other plane. Now these points where this condition is not satisfied, those are called critical points of the transformation. So a critical point of the transformation is where d zeta dz is equal to 0. And so those are the points in which angle is not preserved. For example, if you take zeta equals z to the power n, d zeta dz is n times z to the power n minus 1. So this is non-zero everywhere except at the origin. At the origin this becomes 0. So this d zeta dz becomes 0. So that means it's conformal everywhere except at z equals 0. So z equals 0 becomes a critical point. So what happens is exactly at z equals 0, if you use this transformation, let's say this is zeta equals z to the power n with n equals 2. Right, so this is zeta equals z squared. So if you take two lines, two rays coming out of the origin, one ray is at an angle theta 1, the other ray is at an angle theta 2. If you transform this with zeta equals z squared, this angle will become, this first ray will be at an angle of 2 theta 1, the second angle will be at an angle of 2 theta 2, so this angle between the two lines is double now. So in other words, it's not conformal, but that is true only at the origin. If you draw some other point here like this, that same point will be maybe here, let's say, and it might be in a different direction, but the angle will be preserved. But at the origin it will not. So at the critical points, the mapping is not conformal. And there is a use for this, and the use for this is in, for example, in setting the trailing edge. So I've been talking about how you can map the circle to an airfoil shape, and that's what we're going to do towards the end of this chapter. And that's called Joukowsky transformation. There are many transformations like that. One example is the Joukowsky transformation. So the problem is, when you want to map the circle to an airfoil, the airfoil has a sharp corner. If you preserve the angles everywhere, you will not, everywhere along the circle, you don't know where do you have sharp corners, right? So if you take a tangent to the circle here, it's 180 degrees. So that's what you'll get at some other point. So if you map this point to this will also be 180. But the point on the circle that maps to the trailing edge, you have to make it non-conformal, because the tangent here, the two sides of the tangent makes an angle 180, but you don't want 180 here, you want a sharp trailing edge. So when you transform a circle to an airfoil, as we'll see soon, we'll use a critical point at this point. So this point will transform to this, but that will be a critical point of the transformation, so you will end up morphing the circle at this point of the circle will get morphed to a sharp trailing edge. Okay, so how does all this connect to flow, two-dimensional flow? We saw that an analytic function is the real and the imaginary parts of an analytic function satisfy Laplace's equation, right? So let me see if I can find that page. So we saw this in the last class. The properties exhibited by the real and imaginary parts of an analytic function are exactly the same as the properties exhibited by velocity potential and stream function. So that's why analytic functions can be used to represent flows. And now we are going to go into those details. So two-dimensional flow and complex variable. So we are going to introduce something called complex potential and complex velocity. This is essentially combining stream function, complex potential, combined stream function, and velocity potential. So it's defined like this. F of z is phi z plus I psi z. So remember, phi is velocity potential and psi is stream function. Okay, so we define a complex potential that is velocity potential plus I times stream function. If you take the derivative of that, derivative of f of z is df dz, or f prime, is d phi dx plus I times d psi dx. So if you use x as the direction in which you take the derivative, or you can use y as the direction in which you can take the derivative, and that is, it's the same as d psi dy minus I d phi dy. Right, so essentially these are both the same as u minus iv, where u is the x component of the velocity, v is the y component of the velocity. So we can actually define complex velocity as w, capital W. W is a function of z, and that's just u minus iv, where u is a function of z and v is also a function of z. Or in other words, u is a function of xy and v is a function of xy. Right, so this satisfies what we have known earlier, that u is d phi dx, which is also d psi dy, and v is d phi dy, which is also minus d psi dx. So essentially what we are getting at is the derivative of the complex potential is the complex velocity. And the f of z and w of z are both analytic functions of z. Okay, so because analytic functions satisfy those properties of stream function and velocity potential. So these things are pretty abstract in some ways. It takes a while to understand them, and there's probably so much in this that I've only scratched the surface myself, because it becomes, it requires very abstract thinking. You can see by the time we get to Joukowsky transformation, you'll be like, how in the world did they even think of doing all these things and finally getting flow around an airfoil this way? It's much more mathematical than engineering. But once you understand it and understand the power, it's actually really cool stuff. So maybe the way to think about these things is to try to think of some simple flows and simple functions and what flows they represent. So we are going to take this general format of complex velocity w is a times z to the power n. So z is the xy plane, and this is the velocity, complex velocity, u minus iv. Right, we're going to call that a times z to the power n, and a is some complex number, n is some integer, and we'll vary the n to various different values to see what these flows look like. So we'll start off with n equals 0. Right, so z to the power 0 is just 1, so complex velocity is just a. And so whatever, the a is a complex number, and that will turn out to be equal to u minus iv. And the complex potential is a times z, so the derivative of a times z is a. df dz is a. So it makes sense. So complex potential is phi plus I psi. So let's take an example to put this into some sort of graphical format. Let's take a as some complex number. We're going to say a is 5 minus I times 5. So that is the w, that's the complex velocity. And so this is u minus iv. This just means u equals 5, v equals 5 everywhere. Anywhere you go on the xy plane, that's what it is. And so that's essentially like flow at 45 degrees in this direction, right? So this is the these are the streamlines of the flow. And if you take the complex potential A times Z, that becomes 5 minus I times 5Z. So you set this to different values and you'll get different, this imaginary part will be streamlines, the real part will be the velocity potential, isopotential lines. Okay, so you should actually go and play with this, just like sketch it, put some different values, and then you'll start saying, oh, this is what it means. So until you do that, it's just going to kind of flow past you without you absorbing too much. Okay, so that was n equals 0. Now let's put n equals 1. So n equals 1 means velocity potential is A times Z. And remember, velocity potential, complex potential is, sorry, no, I didn't say velocity potential, it's complex velocity. So complex velocity, W is A times Z, and that is U minus IV, and A times Z is X plus IY, so it's A times X plus IY. Complex potential is a function that if you take the derivative with Z, you will get this, right? So that is A times Z squared over 2, and which turns out to be this in XY notation. So what kind of a flow is this? It turns out that this is the flow, this is the sort of like a stagnation point type of flow. So here it's a flow like this. So let me just say that. So these are the streamlines. Okay, so it's a flow approaching a wall. So these are the psi equals constant lines. So these are streamlines. And these are the velocity potential lines, isopotential lines, phi equals constant. So these lines are actually phi equals constant and psi equals constant lines are rectangular hyperbolas. So this is a stagnation point flow, and one way to think about this is, let's say you have an airfoil and you have the stagnation point, right? So you have the stagnation streamline coming and hitting the airfoil and becoming zero velocity there. The neighboring streamlines become like this. So if you zoom in close into this area, this flow resembles the flow, the stagnation point flow. So my student actually, my recent PhD graduate, Aditya Saini, he actually uses this mapping to, he transforms this, and others have done it too. So he transforms this mapping, right? So this is the flow. If you transform it using some function, you can get flow past a parabola. So let's say the origin is here. So if this point is not at the origin, you'll get stagnation flow past a parabola if you use a function, if you use a correct function. So he uses this to get an analytic description of the flow around the leading edge of an airfoil. So most airfoils, you can approximate the leading edge region as a parabola. So if you just take this. And what he was doing is he was trying to see if you can put like 5 pressure sensors right at the leading edge. Can you measure angle of attack? So in real time. So let's say you have an aircraft flying or a wind turbine blade that's spinning around. One of the big problems is, how do you know what angle of attack that section is operating at? That's actually a very hard thing to measure. People have put all kinds of things. They've put probes here and they've put angle of attack measurement devices. But then that is going to get corrupted by the airfoil flow itself. So what we came up with was an idea where you can embed 5 pressure transducers or pressure sensors, and by having the analytic flow past the leading edge and with some prior calibration, you can say this is the angle of attack. So anyway, those are the kinds of things you can do by having closed form solutions. Okay, so like that you can do other things. So if you have n greater than 1, this becomes the flow in a corner. So depending on how big you make the n, this angle will change. And if you have n equals -1, now suddenly you get flow due to a source at the origin. So -1 is a z to the power -1. So complex velocity is a over z, which is u minus iv. And so z can be written as r times cosine theta plus I sine theta. So if you put that together, you get this. And the complex potential is a times log z, which is this. And so this essentially becomes flow due to source at the origin, and the strength of the source is q is 2 pi a. So the a that you choose here, that will determine the source strength. That's 4. Now, then 4b is where a is a pure imaginary number. So let's call it I times b. This becomes flow due to a vortex at the origin of strength minus 2 pi b. So all those things we looked at earlier, elementary flows, we are now looking at the same things, but in terms of complex analytic functions. And if you put n equals -2, you get flow due to a doublet. Okay, I'm not going through all the details, but you can see if you compare this with what we did earlier for vortex and doublet, this is flow due to a doublet. And now you can start combining flows. And so superposition is possible. That's because all of these flows satisfy Laplace's equation. That means you can add them up. And so you can simulate flow past complicated shapes, potential flow past a complicated shape. For example, if you add the flow due to uniform flow and the doublet, you'll get flow past a circular cylinder. So this is the analytic function that describes complex potential for flow past a cylinder. In fact, if you go and plot this in MATLAB for various values of z, the imaginary part will turn out to be these streamlines, which is cool. It's just like one simple equation and you're getting the streamlines past a circular cylinder. Okay, so that was a quick run through what is the connection between analytic functions and two-dimensional potential flows. So now we are going to go to mapping. We're going to go to mapping of flows. So eventually that's what we want to do, right? We want to take flow past a circular cylinder and morph it and make it flow past an airfoil. So this is what we want to determine. We want to determine flow past some airfoil. And that airfoil plane will be called the z-plane. So we want to determine the flow field around this complicated shape. The airfoil is in the z-plane and the complex potential is going to be some function of z. So f of z is phi plus I psi. That's what we want to determine because we want to see what is the flow past an airfoil. So if we figure this out, we have found out the flow past an airfoil. What we want to do is use a well-known flow and transform it. And one well-known flow is the flow past a circular cylinder. Right? So this flow is, we know this. If you add free stream and double it, you'll get non-lifting flow or flow past a non-lifting cylinder. If you add free stream and double it and a vortex, you'll get flow past a lifting cylinder. And it's just a matter of adding the complex functions like we did 2 pages back. Here we added free stream and double it and we got this flow. So if you put a vortex, you'll get some kind of flow like this, some lifting flow solution, lifting cylinder solution. And we are going to call this the zeta plane, or you can think of it as the circle plane. So this is the plane in which we'll put the circle and the flow around the circle, and the z plane is the plane in which we'll put the airfoil and the flow around the airfoil. So the complex potential here for this flow is F tilde, which is a function of zeta. So this is the zeta plane. So F tilde is the complex potential of the flow around this shape, and that is phi tilde plus I times psi tilde. And we are using tildes because we want to not get confused with the F that's used in the z plane. The symbols, in the previous page I said F of z is phi plus Iz. So this is a different function, right? This is a function that gives the flow around this shape. Just to avoid getting confused, we can't use the same symbol for different things, so we are putting a tilde to denote the flow in the zeta plane. So F tilde is phi tilde plus I times psi tilde. And that is the complex potential for this flow. So we are trying to see if we can get a transformation function that connects these two shapes. So zeta plane is the circle plane, z plane is the airfoil plane, and so we want to see if we can find z as a function of zeta. Or in other words, z is x plus iy, so x is a function of zeta and y is a function of zeta. And so this has to be an analytic function. Okay, that means in the zeta plane we have a circle, and let's say you have some point which is psi plus I eta, right? That's this. And let's say the velocity, potential and stream function are given by these numbers. So phi is the velocity potential is 5 and stream function here is 2. If we do this transformation correctly, and let's say this circle becomes some airfoil shape here, this point will get mapped to this point, right, due to this function. Then the value of the velocity potential and stream function will be exactly the same as this. So phi, which is the velocity potential of this flow at this point, will be 5, just like this value, and psi will be 2, just like this psi tilde is 2 at this point. So in other words, we want a function that will do this. Phi, which is a function of xy, will be equal to phi tilde at the corresponding psi and eta. So if you take this x and y and make it psi and eta, going from the z plane to zeta plane, the phi will be the same and the psi will be the same. So that's what we want. So the complex potential in the airfoil plane is f of z, which is phi plus I psi. If you take the derivative will be the complex velocity, but f of z is analytic everywhere where dz d eta is not equal to 0. So the magnitude of dz d zeta, as long as it's not equal to 0, f of z is analytic. So that means z of zeta, as long as z of zeta is not a critical point, the transformation is analytic. So what we're going to do is we set f tilde of zeta is equal to f of z. So this is velocity potential or complex potential in circle plane, and this is complex potential in airfoil plane. So f of z can be written as f of z of zeta. So remember we had a conclusion from, I think it was in the last class, where we said an analytic function of another analytic function is also analytic, right? So that means this is an analytic function and this is an analytic function, so this whole thing is analytic. So you can get the derivative df tilde over d zeta. This is the complex velocity in the zeta plane, and that's written as w tilde as a function of zeta. And df dz is the complex velocity in the z plane, that's w of z. So df tilde d zeta is df dz times d zeta dz, or in other words, w tilde is w times dz d eta. Or you can write it the other way around. Wz is w tilde divided by d zeta, dz d zeta. There's a lot of these alphabets and Greek alphabets and tildes floating around, and I'm going to get tired talking about all this. Okay, so like I said, this is the sort of stuff that takes time to absorb. But I'm trying to give highlights to the extent possible, focus on the highlights. So the problem arises when the denominator goes to 0. Okay, so here we have complex velocity in the z plane is complex velocity in the zeta plane divided by d zeta dz. And this works fine as long as denominator is not 0. But if denominator becomes 0, then that's a critical point in the flow. So when you do these transformations, you have to choose them such that either the critical point is not in the region of interest, or the velocity in the zeta plane at the critical point is equal to 0. So this is the complex velocity in the zeta plane. Which is the circle plane. So remember, we need a critical point, right? Why do we need the critical point? Yeah, because we have to have a sharp trailing edge, otherwise it's going to become a sort of rounded trailing edge, which is not a typical airfoil shape. So we have to have a critical point. So when we do the airfoil transformation using Joukowsky or other transformations, let's say this point gets mapped to the trailing edge. We don't want this angle to be conformal because this angle is pi, but this angle is not pi. We want it to be something else. So the only way to do that is to put the critical point here. Only then you'll get a sharp trailing edge. But if you put the critical point there, your velocity is going to go, velocity is not going to work out, because w of z is w tilde of zeta divided by dz d eta or dz d zeta, and if this becomes 0, this is infinite velocity at the trailing edge. So the only thing you can do is if whatever point you choose on the circle to map to the trailing edge, you have to make sure the velocity there is 0. If the velocity is 0, then this velocity here will become we won't become infinity. It will become finite. Okay, so So this we have seen. So when we do the transformation of flow past a circular cylinder, the point that we want to become the trailing edge in the airfoil, let's say that point will be a stagnation point. So let's say when you want flow past a lifting airfoil, you have to take a flow past a lifting cylinder. So lifting flow past a cylinder. And so this is how the lifting flow past a cylinder is, right? It's free U infinity plus doublet plus vortex. So, and you get two stagnation points, right? So the rear stagnation point is the point that will transform to the trailing edge. This point zeta of t maps to the airfoil trailing edge. Eventually, we haven't got to it yet, but we are trying to say these are all the things we have to do in order to make that work. Okay, so that's how we're going to map the flow and get flow past an airfoil. And one of the early transformations to get flow past an airfoil was done by Joukowsky, I believe Russian mathematician, aerodynamicist, fluid dynamicist. So he came up with this transformation. It's just as simple as this. Z of zeta is zeta plus c squared over zeta. And this is the Joukowsky transformation. And this transformation, so essentially if you have a circle in the zeta plane, if you apply this transformation and do different things, on the z plane you will get something resembling an airfoil. Okay, so let's see how that works out. Okay, so we are going to take a circle in the zeta plane, but we are not going to put the circle at the origin. We'll put the circle offset from the origin, and the center of the circle will be here. So this is the origin. So this is the zeta plane, right? And so the x-axis or the horizontal axis is psi and the vertical axis is eta. The center of the circle is here. The radius of the circle is a. So radius of the circle is a. Center is at this point. And if you think through it, the equation for the circle in complex variables is mu plus a times e to the power I theta. So if this is really hard for you to follow, you really need to look at those 2 pages of complex variables review that I put on Moodle. Okay, then I think it'll start to become easier. So essentially what we are saying is a e to the power I theta, so this is theta, is this vector. Okay, and so we are saying this vector plus this vector for various values of theta will give this circle. So this vector is mu, that's the first part, plus a times e to the power I theta. For different values of theta, it's like you take this vector and spin it around about this point, right? But then when you add them up, you get a circle that's displaced from the origin. Now, where the circle intersects the horizontal axis, zeta, is this point we are going to call C, and that point is the one that will get mapped to the trailing edge. And so we have to come up with the function that we use. We'll have to make sure that this is a critical point of the transformation. Okay. So the equation of the circle is this. I've tried to explain this in the next page. Zeta equals u plus mu plus a times e to the power I theta. When you vary the theta from 0 to pi, this will form different points on the circle. So if this is hard to imagine, just go to MATLAB and put one complex number here, another complex number here, and put various values of theta and plot it, and you will see that it's a circle, right? It's that. For some people, these are very hard to visualize, and one of the easy ways to start absorbing this is to go to some software and plot it. So the trailing edge of the airfoil will be mapped to the point C, which is this, which has a coordinate of zeta t. This is zeta t. And we know that the circle has to pass through that point, right? So we are going to write the complex number for the center as follows. So this point that we used to call mu, we are going to write it in exponential form. We're going to write it as m times e to the power I delta. M turns out to be the magnitude of this vector, the position vector of the center of the circle, and delta is the angle that this makes. So if you now connect that with the trailing edge point, the point that becomes the trailing edge. So this is the center, and let's draw a vector from the center to this point. That vector is, so this point is zeta t. So that means this is the zeta t vector. This is the mu vector. And so this vector is zeta t minus mu, and this angle is minus beta. So minus beta turns out to be the argument of this vector, which is the argument of zeta t minus mu. So this is all sort of some mathematical manipulation to make things easy later on. So to make things easy to visualize in the transformation. So now we can write this equation for the circle as follows. Or this is, I guess, the center of this, equation for the I think this is just the equation for the center of the circle. So this is the center of the circle, and that's equal to a times e to the power minus I beta. So that's this minus zeta of t. And that's equal to m times e to the power I delta. And that is the center of the circle. So mu is m times e to the power I delta, and that's equal to a times e to the power minus I beta minus zeta of t. So if I don't look at this for some time, even I have to scratch my head, because I don't do this thing often. Unlike other parts of airfoil aerodynamics, this always takes time to absorb. Okay, so we have the equation for a circle, and the circle is such that the center is at some point here, and the point where the circle intersects the horizontal axis becomes the trailing edge. So the flow around the circle is determined by free stream velocity, angle of attack, and the requirement that this becomes a stagnation point. Right, so let's say you have some velocity, free stream velocity v infinity, and some angle of attack, alpha. If this circle had no lift, then it's straightforward, right? It's just free stream plus a doublet going opposite to the v infinity, that will give the flow past non-lifting cylinder. But we want some sort of a lifting cylinder, and furthermore, we want the stagnation point to be here. Okay, so the flow is modeled using a uniform flow of strength v infinity and some angle alpha, a doublet of strength determined by the radius of the circle. So once you know the radius of the circle, there has to be a certain doublet strength to get this as a streamline, and a vortex that will make sure that the stagnation point is here. So it turns out the flow, for this flow, this amount of circulation that you need is gamma, which is 4 pi a v infinity sine of alpha plus beta. So this is where all these angles come from. So a is the radius of the cylinder, and beta is this angle, this is minus beta. So this angle is minus beta. From 2 pages back. So in other words, if you, and this is radius of the cylinder. So if you take a cylinder and position it such that this is at an angle of minus beta, the v infinity has got some angle alpha, and there's a magnitude. So magnitude is v infinity, angle is alpha, and the radius of the circle is a, then this is the vortex strength you need to satisfy that. And you can now use Kutta-Joukowski theorem, because if you know this, you can get the lift. So lift per unit span is rho v infinity gamma. So that is rho v infinity times gamma from the previous page, and that turns out to be this. And now you can get lift coefficient, which is L prime over half rho v infinity squared c. So you divide this by this denominator, and you now get 8 pi a over c sine of alpha plus beta, where c is the chord. Because this, you have denominator here, right? So we still haven't seen how the airfoil looks, but before we look at the airfoil, we start to see that this is the lift coefficient. We still don't know what the chord is. So we'll see soon that this beta is going to control the airfoil camber, and the chord is going to be approximately 4 times a. A is the radius of the cylinder, and chord will be 4 times that. And therefore, lift coefficient is approximately 2 pi times sine of alpha plus beta. And for small angle, small alpha and beta, this is just 2 pi alpha plus beta, where these are in radians. So this is the difference between thin airfoil theory and this. This is actually a thick airfoil theory, because the theory straight away accounts for thickness. And so you have a correction here. In thin airfoil theory, you just had 2 pi alpha, right? For any camber. Thick airfoil theory corrects that a little bit and says, well, actually there's a little bit of dependence on camber, and that camber dependence comes in from beta and thickness. That's why it's little different from thin airfoil theory, because this is not assuming that thickness is 0. Okay, so let's start looking at how the airfoils will turn out to be. First, the simplest airfoil we get is by putting the circle at the origin. So here we put the circle at the origin, so the radius is a, and this point, the zeta of t is just where the circle intersects the horizontal axis. If you use Joukowski transformation, which is this, and transform this, you will get a flat plate in the airfoil plane. So this is the airfoil plane. Okay, so this chord or this length, so in other words, this point will become this point. So that is at plus 2c. So let's say, I guess, yeah, I think this point is C. Yeah, this point is C. I don't know what this symbol is. If this point is capital C, this point will become plus 2C, and this point will become minus 2C. So this is the chord of the flat plate, which is 4 times C. C here is the, C here is this transformation variable. Anyway, so C is 4 times the radius. So the chord is 4 times the radius. And we can still do free stream coming at an angle of attack. So we can put this V infinity here at some alpha, and we'll get the same flow for this body. So this circle is squished and made into a flat plate, and all the flow around it also will be conformally morphed to get the flow around this. And so if you do the mapping, it will look like this. So flow due to V infinity at some angle of attack around this cylinder. Remember, this is a lifting flow. Even though it's a flat plate flow, it's a lifting flow because we are forcing the stagnation point, rear stagnation point to be here. And this flow will actually get morphed to this, which is the potential flow past a thin flat plate. Okay, so that's what happens when you put the circle at the origin. Now you move the circle a little bit up and you get a circular arc camber line. So here we have taken that same circle, we have moved the center above the origin on the imaginary axis. So center is at m e to the power I times pi over 2, which is I times m. And beta is not equal to 0, right? This is beta. So if you transform this using that same Joukowsky transformation, you get the circle will get mapped to this. So all the points on this side will get mapped to the upper surface. All the points on the lower thing will get mapped to the lower surface, but it's the same contour. So this is a circular arc. It's an arc of a circle. If you just draw this whole thing, it'll be a circle, but we are only looking at this geometry. And so the 2 points extremities are minus 2c and plus 2c. And so the chord of the airfoil is 4 times c, and c is this variable of the transformation. And the maximum height is 2 times m, which is the m used here in the circle. And so the maximum camber to chord ratio is 2m over 4c, or half of tan beta, which is this is the beta. And so again, flow past, you can take the flow past the cylinder, and it will be flow past this circular arc, including the lifting component. Now we moved the circle up, right? If you move the circle to the left, you will get a thick symmetrical airfoil. Okay, so we take this, move it to the left, put the center along the negative real axis. You pass it through the transformation, and you'll get an airfoil like this. It's a symmetric airfoil and it's thick, and the chord is going to be 4 times c times power series. So approximately this is going to be very close to 1. So this chord will be close to 4 times c. And thickness to chord ratio will be 1.299 epsilon, and that epsilon is this. The m that we use, it's a ratio between m and the transformation and this point c. Okay, so again, you can get lifting flow past this symmetric airfoil, and so if you map the flow, it will look something like this. Okay, so this is the lifting flow past a thick symmetric airfoil. Now we do the combination of the previous things, right? If you moved it up, you get a thin camber line. If you moved it to the left, you get a thick airfoil. If you move it up and left, you'll get a thick cambered airfoil. It's just mind-boggling. How did they think of all this? I mean, I go through this in the course, but it's one thing to go through what somebody else has done, but another thing to actually be the first person to come up with that. Anyway, so here we put the airfoil at negative real plus positive imaginary part, like put the circle here, center here, go through this transformation, and you get a thick cambered airfoil. And so Joukowsky transformation gives the exact solution for a cambered thick airfoil. Unlike thin airfoil theory, there it was an assumption that there's no thickness and camber is small. Here, this camber is not necessarily small. So this is an exact solution for a cambered thick airfoil. So what I've done, and I think I'll put this on Moodle. I have to put this on. It's probably already on Moodle. If not, I'll put it now. So I wrote a quick program to transform a circle to an airfoil by choosing various points for the center of the circle, and the program will output something like this. So this is the circle, and can you see this? I'll put both of these on Moodle. So the center is this point. This is the center, this is the origin, and here I've moved the center to the left and up, right? And when you transform it, this becomes the airfoil. So the origin of the airfoil is here. So that's one of the problems. With transformation, the origin is not at the leading edge. We do that in aerodynamics for convenience, but in the transformation it will come out to be here. And you can always scale it and rotate it and put the airfoil the normal way later on. But anyway, this is what you get. And so this theory actually gives flow solution, and it gives lift and pitching moment and potential flow, which is really really powerful thing. So the whole of Profile is built on transformations like this. So with this, I'm going to wrap up conformal mapping and Joukowsky transformation. So we have one more class on Thursday, and that's when I'll finish up a couple of remaining topics in thin airfoil theory, and we can talk about other questions if you have. Okay, so we'll stop today. Thanks.